Oh, we got sitting over right now. In the medics. I can't see it. I think I'm gonna move to the protocol. Oh, yeah. It's a moving spots. You need to sit like right in front of the desk, so we can't see anything. You know, Angel, right? They go next to the seat. Oh, yeah. What you call it? Yeah, bigger and right in front of you, but it's the cat's. That's true. Oh, look at the board and I I'm like, yeah, like, it's there. And then, if you were to do it, yeah. I have passion. Solid mechanics. I think that's intro or solid. Solid. Yeah, it's just an instrument. It's like climbing. If you're the slider, hey, Bill. You're gonna go kind of choose like one of them.
We're only on day 2.
Yesterday was my birthday, and then today we.
Oh, okay. Well, happy belated birthday.
Where do you?
Oh, yeah. I know that's how I can.
It's weird. I watched like full like it's like
While he's on fucking duty, whatever.
another eight. So like, oh, I'll still be on
Yeah, we need it.
Well, Andrew.
I'm probably gonna be my name. To somebody.
Probably gonna be right now. How you going? Oh, sit down. I'll sit back.
Man, no, I'm
Hey, how's it going?
It's Thursday. I thought yesterday was Thursday. I woke up and I was like, I feel all over it yesterday.
Well,
I thought yesterday was Thursday and I was like, it's the weekend.
there next
Oh
time.
my gosh, we have to do all of it.
It's almost, you know, knowledge and experience, you know?
Oh, yeah. Damn. Damn. I'm sorry, bro. Hey. Hi, Brian.
Not switching, what no up to? This morning. This is why I want to. Do you know this color? You said this against speed. That's just funny.
That's what I'm saying. My friends like, hey, let's go to different.
I got a 78 on. Oh, really?
And they've changed that. Like, it's not-
Yeah, but that's on Tuesday. My shit.
I'm also distracted.
No, Monday, just Tuesday. Yeah, it's just clutch, huh?
I just know the subject was called. It was
Finals, I know. Like, because of what you said, like.
It's a morning.
I know that you.
Yeah, louder now.
Friday.
No, I have been.
Yes.
I feel like it's.
3 hours.
It is
Like,
gonna
I
be
think we
busy.
got out like with like 30 minutes.
Get out of here. 3 hours.
Because she was going over. MATLAB stuff, going over every line.
I don't need her to teach me MATLAB. I've been using it for like 2 years now.
It was going to.
Things
I'm gonna just try to learn how to go about it, but.
Oh my God.
Around maybe it's around 30. There's something if you guys are like, I like to do that shit, like, right in the first. I'll be working at school at 8:30.
Yeah, then I gotta wait a couple.
Right now, I got shit to do. I'm rewatching. Yeah.
Yeah, I don't
Steve Harvey or Bobby Murphy.
Yeah, that was mustache.
Oh, it works.
And Americano. They did good choosing venue for what's his name? Pedro Pascal.
Yeah, that's it.
Yeah, that was cool. I like that.
Figure out here.
Yeah.
She change anything?
No. I mean, are you able to like finish? Are you?
Yes, it is. No, it's in Spanish. I don't know much about it.
Nah, I watch it like you. I mean, there's some videos in Spanish.
There's a lot of checker. Reading code.
Yeah, it's actually kind of good that it really shrunk down like that, but it's in the bottom.
That was what I was hoping.
But I think.
You want a longer one? How do you do this? Schedule is calendar.
Yeah, so like I work like in my.
Like your club or the story and your classes and everything. Right here. I can meet you for 2 or 3 minutes.
Like, I just like for like the same time. I was like,
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Thanks for asking. All right, it's day 2 of a heat transfer. So today is the, I guess, first real lecture. So we're going to be taking notes. So like I mentioned on Tuesday, you can see here we have the learning objectives for today. So we're going to go over all this. I don't know if we're going to get I don't know if we're going to get to thermal resistances today, but we'll kind of do our best. Okay. Okay, so some announcements before we begin today. I did post your guys' first problem set yesterday afternoon. You probably can't do any of it right now because we haven't really learned any heat transfer yet, but I would definitely take a look. And then over the next couple lectures, that should become more clear to you. So it's due not next Thursday, but the Thursday after that. So you have 2 weeks to work on that first problem set. Okay. Okay. So I think that's it for announcements. Are there any questions I can answer before we get started? Yep.
Are all your notes going to be like handwritten or?
Yes.
Okay.
Yeah. So this is how I usually lecture. So I have my iPad here. I project it onto the screen and I handwrite it like that.
Okay.
Yep. Okay. All right. So let's go and get started. So we're starting the first unit of heat transfer today, which is conduction heat transfer. Okay. So what is conduction? So we defined conduction on Tuesday, but let's go ahead and refresh our memories. Okay. So conduction is the transport of thermal energy through a stationary medium. Okay. So the operative word here is stationary. And so, whenever you have, two objects or, a temperature difference through a solid, and that solid or the fluid or whatever is not moving, then you're going to have heat transfer through conduction. Okay. And, if you're curious, the way conduction happens is it's through molecule to molecule transport. Okay. So the thing with a medium, and so another word for medium is matter. And so when you have something that's made of matter, you have a lot of molecules that are, kind of jam-packed close to each other. And when you have a temperature difference throughout that medium, then one molecule is going to transfer heat to another molecule, right? So, within the solid like this, you might have a molecule like this, okay? Let's say a bunch of molecules all kind of, lined up together. And so conduction happens when, heat goes from this molecule to this molecule, okay? It's just the fact that, molecules are touching each other. They are, bonded by their electromagnetic forces. That's how conduction happens, okay? Now, as we kind of go through some other definitions today, I want you to kind of remember this because everything kind of comes back to this idea that, conduction occurs through molecule by molecule transport, okay? Okay, so let's start with an equation. So there is an equation that is used to describe the amount of heat transfer that occurs through conduction. And that equation is called Fourier's law. Okay. It's actually just called Fourier's law, but Fourier contributed in a lot of different areas. So I want to be specific. Say this is Fourier's law for heat conduction. Okay, it's a fairly simple formula. It basically says that Q is equal to minus K times A times dt dx. Okay. And of course, we're going to define every single term in this expression here. Okay. Okay. So what do all these terms mean? Let's start with Q. So we'll go from left to right. Okay. Q here is this is a symbol that you'll see a lot throughout this class. Q here stands for the heat transfer rate. Okay. And the units for heat transfer rate is watts, or W. Okay. And remember, watts is nothing more than just joules per second. Okay. Joules being a unit of energy, seconds being a unit of time. So watt is a unit of power. Okay. Okay. Let's define the next term in this expression here. So let's look at K. So K here is the thermal, what's called the thermal conductivity. Okay. This is a property of the material itself. So whatever type of solid that we have, thermal conductivity is a material property very similar to like density or Young's modulus. Okay. You probably haven't seen it before in a previous class just because you haven't taken a heat transfer class. But this is right in that kind of material properties. Okay. So this is property of material. And of course, we have units for this. Probably one of the more annoying parts of this class is that we use thermal conductivity a lot, but the units are not really exactly convenient. So the units for thermal conductivity is watts over meters, degrees Celsius. Okay. You're going to be writing that a lot in this class, so get used to it. Okay. Okay, so basically that tells you that, the thermal conductivity tells you how much or how quickly energy can transfer through that material. So watts is in the numerator, and then on the denominator we have meters and degrees Celsius. Okay. Okay. A. Area. Area. A is area. Very good. Okay. Specifically, it is cross-sectional area. Okay. So cross-sectional basically mean that's the area that's perpendicular to the direction of heat transfer. Okay. And we all know the units for area. So area is meter square. Okay. Pretty straightforward. And then finally, we come up to this guy right here, which is a derivative term. So dt dx right here is what we call the temperature gradient. Okay. So the temperature gradient describes a change, basically describes a difference in temperature across a distance. Got greedy, I could fit distance in there, but that last word there is distance. Okay, and so the units for this is just temperatures over length, and so there's actually a few different units for temperature, probably as you remember from thermodynamics. So I'm going to use I'm going to try to use degrees Celsius as much as I can because I think that's the most easy, that's the most straightforward one. But degrees Celsius and Kelvin are kind of interchangeable. So you might see me use K, but we have K in this expression here. So I'm going to use degrees Celsius. Okay. And then in the denominator, we have meters. Okay. Okay. So, just like, just because this is the first equation that we're kind of introduced to here in heat transfer, let's kind of dissect this, okay? So it's a fairly straightforward equation. So everything is kind of multiplied by each other. But, whenever you have an equation like this in kind of an engineering class, it's always good to think about, how do each of the terms kind of affect each other, okay? So I always like to do this. I like to kind of dissect the equations. So on one side of the equation here, we have the heat transfer rate. It's kind of by itself, okay? And so this equation here is basically a formula to compute that heat transfer rate. So a good thing to do is just think about, how do each of these properties here, how do they affect how much heat gets transferred, okay? Okay, so let's talk about the thermal conductivity first, right? So if you look and see where the thermal conductivity is in relation to the heat transfer rate, you'll see that they're both kind of proportional to each other, right? So they're both kind of on equal sides. They're both on the same side of the equal sign, okay? They're on different sides of the equal sign, but they're both in the numerator. So basically what this tells us is that the higher the thermal conductivity, the more heat transfer is going to occur. Okay. So if you have a material that has a higher thermal conductivity, that means that heat is going to flow much more easily in that material, okay? By the way, I know everyone noticed the negative sign. I'll go over the negative sign in a second. That negative sign there is actually meant to interact with the temperature gradient. We'll come back to it, okay? Okay. So let's take a moment to talk about, what kinds of materials or what kinds of, mediums have a high thermal conductivity. Okay. So generally speaking, solids will have higher thermal conductivities than liquids, and liquids will have higher thermal conductivities than gases. Okay. Because remember how conduction occurs. Conduction is the transfer of heat between neighboring molecules, okay? When you have a solid, those molecules are all kind of stationary in kind of one place. So it's very easy for heat to transfer in between them. When you get to liquids and you get to gases, the molecules are kind of moving past each other a lot. And so it's a little bit more difficult for heat to kind of move in between them, okay? Gases in particular, because in a gas, the molecules are often very far apart from each other. So, it's often very difficult for them to pass pass heat to each other, okay? Now, I did say this is generally true. There are situations where some liquids have a higher thermal conductivity than some solids. So a very common example of this is liquid mercury. So liquid mercury is very, well, it's liquid. That's why it's called liquid mercury, and has a very high thermal conductivity, often higher than a lot of, general solids, okay? Another interesting trend among thermal conductivity is that generally for solids, and I guess, liquid solids as well, the thermal conductivity of metals is generally higher than that of nonmetals. Okay. And why is that? So in a metal, probably you remember from your solid mechanics classes, metals, they're inside a metal, the molecules are very tightly kind of packed and very tightly organized. And so there's a lot of pathways and a lot of easy ways for thermal energy to move through a metal versus non-metals where it can be a little bit more disorganized, okay? And hopefully, this kind of, aligns with what you kind of generally understand about heat as well, right? If you have a vessel for holding hot liquid, so say like a mug, right? You don't see very many mugs made of metal out there because if you had a mug made of metal, heat is going to flow through that metal very easily. So as soon as you pour your hot coffee into the mug, you grab it with your hand, and now you have second-degree burns, which is not fun. Generally speaking, a lot of mugs or a lot of objects that are meant to handle heat are made of something like ceramic, which is a non-metal, which is known for being very insulating. Okay. Okay. So that's thermal conductivity. So the higher the thermal conductivity, the more easily heat can transfer within that medium. Okay. Any questions on this so far? Okay, good. Okay, let's look at the next property here. So let's look at the cross-sectional area. Okay. Okay. And so let's look and see where the cross-sectional area is relative to the other terms in our Fourier's law. Okay. So you see here that cross-sectional area is, right next to the thermal conductivity. And so what this is telling us is that the higher the cross-sectional area, the more easily heat can transfer within that medium. So this one hopefully is pretty, straightforward as well. So heat is not some mystical thing. It's bound by the laws of physics, like most things in this world. And so if you give it more avenues or more pathways to travel, it's going to make it easier to go. Okay. So let me give you an analogy that hopefully everyone here can relate to as a resident of Southern California. Right? And so generally speaking, when you're driving on a freeway, the more lanes there are on the freeway, the more easily it is for traffic to flow. Right. So there's almost always pressure from the public to expand the freeways out by one extra lane just because, traffic just gets crazy in Southern California, right? So, you can think of the addition of more lanes to be analogous to a higher cross-sectional area, right? So higher cross-sectional area, more lanes for the heat to go, more heat can flow, okay? All right. Now let's look at the last term here on the right-hand side. So the last term on the right-hand side is the temperature gradient. Okay. So this is probably the term there that's probably the most mysterious out of all of them. So let's take a moment to kind of define this. Okay, the temperature gradient here represents a difference in temperature across a certain distance. Okay. Remember what we said on Tuesday. So we said Tuesday that heat transfer will always occur between something that's hot and something that's cool. right? When you have something that's hot, that usually means it's at a higher temperature. Something that's cool is at a lower temperature, right? Okay. So let me just kind of show you exactly kind of what that term or how we kind of compute that term, okay? So if you think back to your calculus courses, a derivative like this, dt dx, basically just means a change in temperature over a change in distance, okay? Let me illustrate something like that for you. Okay, so let's say we have a cylinder here, okay? Let's say that the left-hand side of the cylinder is at 100 degrees Celsius. And then the right-hand side of the cylinder is at room temperature. So we'll say it's at 25 degrees Celsius. Okay. Now, intuitively, we have a hot side and a cold side. So what we generally expect here is that heat is going to go from left to right. Okay. So this is the direction of Q. Oh, let me give you the length of the cylinder as well. Oh. Okay. So let's take this situation and let's compute the temperature gradient for this cylinder here, right? So if I call the left-hand side, we'll call the left-hand side side 1. We'll call the right-hand side side 2, okay? So that means T1 is going to be 100 degrees C. T2 is going to be 25 degrees C, okay? We need to define the x coordinate for both sides too. So we'll assume that the left-hand side is our origin. So we'll say x1 is equal to 0, and x2 is equal to L. Okay. So let's compute the change in temperature. So change in temperature is the temperature on the right-hand side minus the left-hand side. Or you can do left minus right, as long as you're consistent, okay? But I'll define delta T to be T2 minus T1, okay? Because that's generally the convention that we use in math. And then delta X here will be same ordering. So X2 minus X1. All right, so let's go ahead and plug in. So T2 here we know is 25 degrees C, and T1 is 100 degrees C. Okay. And then X2, well, I should have given L a number, but that's fine. So X2 here is L, and X1 is 0. Okay. What's up?
So the negative.
Exactly, yeah. So if you compute this, you're going to see that we actually have a negative number, right? So we have minus 75 over L, okay? So if you think about kind of the traditional kind of, X direction where going to the right is positive, right? We know, but we just know from intuition that heat should actually go from left to right, right? So heat should actually go from the hot side to the cold side. But when we compute the temperature gradient here, we actually get a negative sign, which seems to imply that heat's going from right to left. Okay? So to kind of rectify this, if you go back to the original Fourier's law, you'll see that we have this negative here. Okay. So that negative here, back in Fourier's law, is meant to counteract the fact that normally when we compute temperature gradient, the direction is kind of opposite. Okay. Let's see, so we add. Okay. So usually when we compute temperature gradients, it's always kind of opposite of what we kind of naturally think of which direction heat should go. So we add a negative in Fourier's law to counteract that. Okay. All right, and so that's Fourier's law. So that's our first equation. We'll be using this one a lot, but I spend quite a bit of time on this one just to just because this is everyone's kind of first time with heat transfer. So this is kind of the time when we should start building our intuition in terms of how things. Okay. Any questions on this? Okay, good. All right. So let's move on to the next equation, which is very aptly called the heat equation. Okay. And I added the there because it's the heat equation, right? It's a very important equation, so it deserves some respect. So we should call it the heat equation. For a lot of mathematicians, actually, and a lot of engineers, the heat equation is actually their favorite equation. And maybe you guys will see, maybe not, but it's a very nice equation in terms of how it behaves. Okay. Okay. So the heat equation is something that's used a lot in engineering, because a lot of times, when we're doing thermal engineering, one thing that we're curious about is we want to find out how temperature is distributed in a given material. Okay. So let me go ahead and draw our cylinder again. Okay. So let's look at our, we'll say that the left-hand side, once again, is 100 degrees C. Right-hand side is 25 degrees C. Okay. Right. We know what temperature the end caps are. And in fact, this is quite common, just because thermometers are a thing. And oftentimes you can put a thermometer onto an object to see how hot it is. Okay. But what's difficult, or what's not always easy, is to see, what is the temperature inside this material? Okay. Or, what is the temperature at this point? Or what is the temperature at this point, right? Because oftentimes, it's not always easy to stick thermometers or stick probes inside a material. And so oftentimes we have to rely on modeling. We have to rely on math to compute these things, okay? And oftentimes this is important because you want to find out what the temperature is inside, because that's going to be critical to, your thermal engineering. And so the heat equation allows us to compute this. Okay. So I'm not going to derive the equation just because that would take quite a while. So I'm just going to give it to you, but I'll give you some notes in terms of how this equation is derived. If you remember from your fluids class, you remember from your solid mechanics class, it's hopefully shouldn't be too much of a leap in logic. It's basically we're taking conservation of energy and applying it on a infinitesimally small solid. Okay. But let me go ahead and give you the equation here. It's actually a partial differential equation, which, don't worry, we're not going to solve a PDE in this class. That's for grad students. Okay. So you can see we have a lot of derivatives here, but the fact that we have multiple independent variables, we have both x and t, we have to use partial derivatives. Okay. Okay. So once again, let's go through each of these terms here and define kind of how they or define what they actually mean. Okay, so let's look at the spatial derivative first. So let's look at partial t, partial x, partial squared t, partial x squared. Okay. All right. So this term right here determines how temperature varies in space. Okay. So when you go from one point to another point, this term here basically determines how temperature is going to vary in that space. Okay. It's a second derivative, and second derivatives have a very important property in kind of applied mathematics. So this tells us that temperature is actually going to follow what's called a diffusion behavior. So if you haven't heard the term diffusion before, diffusion basically just means a slow spread, just purely by concentration. Okay. Or I should say slow passive spread. The best analogy I can give for for diffusion is, let's say that you have a glass of water. It's completely still, so you're not stirring it or anything like that. So let's say that you drop a little droplet of dye in there, right? So what do you expect to happen? So as soon as the dye drops in, actually, let me draw it here too. Okay. So we have our cup of water here. Okay. And then at a certain point, let's say that we drop a little thing of dye in here, right? So the dye kind of starts at this point right here. Okay. What do you expect to happen? So let's say that you don't stir it, you just kind of leave it alone and you just watch it. Okay. Generally, what you expect to occur is that, at first, the dye is going to be concentrated at just kind of one small location in the cup, right? But then over time, right, if you just let it sit there, through diffusion, that dye is going to spread out to every single corner of the glass. Okay. Okay. Now it's not going to happen right away, right? It takes time for diffusion to occur, but eventually, if you give it enough time, it's going to spread. Okay. Also, when it spreads, you're going to notice that it also dilutes, right? So, as the dye gets to kind of the corners here, it's not going to be as intense. It's not going to be as bright as it was up there. It's going to be kind of a little bit faded down here. Okay. That's diffusion in a nutshell. And so the heat equation tells us that temperature follows that same idea. And so, if you have a hot object in a cool environment, eventually that cool environment is going to heat up because the heat from that hot object is going to diffuse out throughout the rest of the environment. Okay. So, this is kind of a very important part of the heat equation, that temperature will diffuse out in or spread passively in space. Okay. And we'll see this through our couple of examples that we're going to do right after this. All right. Any questions on this? Okay. Good. Okay, so let's look at the next term. So the next term that we have in this equation is Q dot over K. So K is a familiar face here. So K is our thermal conductivity. Okay, so we've already defined that, so I'm not going to go through it again. Okay. In the numerator here, we have Q dot. So Q dot, this here represents what's called thermal production. Okay. So this right here accounts for situations where you have a material that can generate energy throughout that material. Okay. So basically any material that can either generate thermal energy or even absorb it as well, okay, that's going to affect the temperature distribution. Okay. Now you might be saying, wait a minute, there's this thing called the conservation of energy, which says that energy cannot be created or destroyed. So how can we have a term in the heat equation called thermal production if it's impossible to, produce energy out of nowhere? And you'd be correct, right? So there is no way to create energy out of nothing. But it is possible to, convert energy from one form to another, right? So for example, so let's say that you have a, one thing that probably everyone has used at some point is a heat pack, right? Heat pack has basically stores a lot of chemical energy in how it is kind of designed. And once you kind of crack it or once you kind of open it, that chemical energy is then converted into thermal energy, okay? The thing with heat transfer problems, we only really consider heat energy. And so when you convert energy from one form to another, we consider that as kind of thermal production. So, the name isn't quite the best. We're not actually producing thermal energy. We're mostly just converting it from another energy form to thermal. Okay. Honestly, this situation is not that common. There aren't that many chemically reactive materials that can produce energy. But it is important to kind of account for it mathematically if we do have that situation. Okay. So most of the time we're going to assume that this term is zero. But it is good to kind of know how it affects our results. Okay. All right. Any questions on thermal production? Okay. And then the last term that we have in our equation here is the time derivative. So we have 1 over alpha, partial t, partial big T, partial little t. Okay, so the little t here stands for time. Okay. And so when we have a derivative of temperature with respect to time, this tells us that this is what's called the unsteady term. So in other words, when temperature can change as a function of time in a fixed location, this term here will account for that behavior. Okay. So for now, I would say for the next maybe 3 or 4 weeks, we're going to assume that this term is 0. And so that's kind of all I'll say about it right now. I have a lot more to say about this, but it's only kind of when the time, only when the time is right. So we'll say this goes to 0. Okay. So when you assume that your problem is steady state, or when you assume your situation is steady state means that nothing is changing with time. Then you can kind of cross this one out. And that's all I'll say about that this term here. When we get to unsteady conduction in maybe week 4, week 5, we'll come back to this. But for now, we'll just kind of keep this as it is. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's see how we can actually use the heat equation, to solve a problem. I believe this is our first example of the semester. Okay. So in this example, let's consider the cross section of a window pane. Okay. And let's say that, this window pane is somewhere in Canada. So it's really cold outside and really warm on the inside. We'll say outside the window is cold air. Okay. This example will do all with symbols here. So we'll say the cold air has a temperature of T infinity. Okay. T infinity is usually the symbol that I'll use to describe environmental temperature or temperature of a very wide area. Okay. And then say inside the window is warm air. Okay. So we'll call that Ti. Okay, so Ti for T inside. Okay. Okay. So let's go ahead and draw this. And so, imagine you're kind of looking at a window from the side. So, the thickness of the window is kind of goes from left to right. Okay. So if we look at our window, it looks something like this. Of course, we're zooming in quite a bit just so we can visualize it. Okay. So say the left-hand side of the window is outside, the right-hand side of the window is inside. Okay. We know from the problem that the outside temperature is T infinity. And so we're going to assume that the temperature right at the outside, surface of the window is T infinity. Okay. And then the temperature at the inside surface we'll say is Ti. Okay. Let's say we also know the thickness of this window. So the thickness of the window is given by L. And so basically the distance between the outside and inside temperatures is given by L. Okay. All right. And then since we're going to be solving for an equation here, we need to define our coordinate system. And so let's say that the origin of our coordinate system, or x is equal to 0, is right at that outside edge. Okay. So x is equal to 0 is going to be right at that left edge. Okay. Okay. So what do we want to do for this problem? So let's compute. Let's compute the distribution of temperature within that window pane. So we know the temperatures on the left, we know the temperature on the right. What's the temperature in the middle, or just at any point in the middle, okay? And how we're going to do this is we're going to use the heat equation. All right. Any questions on the problem setup? Okay, good. Okay, so let's start. So let's go ahead and start by writing the heat equation. So I'm going to come back up here. And let's write down this guy down there, because that's where we're going to start. Now, granted, we're going to be canceling a lot of terms here just because of some assumptions that we're going to make. But it's always good practice to start with the full equation and then kind of go from there. So let's start from the full heat equation. Okay. So full heat equation, we have partial squared T, partial x squared plus Q dot over K is equal to 1 over alpha partial T partial little t. Okay. Okay. So let's apply some assumptions and cancel some terms here. All right. So let's look at our problem here, and let's see, what can we cancel out based on what we know about the situation. Okay. All right. So we know that we're working with a window pane here, and so the material that we're working with between T infinity and Ti is probably glass of some kind. Right? Most windows are made of glass. Okay. Right. Generally speaking, glass is an inert material, so it's not reactive. I know nowadays, there's some really crazy material people that are making, glass that can, stream Twitch right now or something like that. But generally speaking, most glass is non-reactive, and so, because we have glass here, right? Pretty safe assumption is that we can say that there's going to be no thermal generation. All right, so first assumption we're going to make here is we're going to say no thermal production. Production generation, I kind of use those terms a little bit interchangeably. So if we have no thermal production, then there's no need for our Q dot term here, right? So we can cancel that term based on our assumption of no thermal production. Okay. Okay. Number two, another assumption that we're going to make here is that we're going to assume that our situation is steady state. And so if our situation is steady state, that means we can take the time derivative and just cancel that person out. Okay. And so our time derivative term is also going to go away. Okay, so we're going to cancel that term by assumption number 2. Okay. All right. So after we apply our assumptions, all that we're left with is the following. Okay. And since we canceled the time derivative term, what we can do, so this is just kind of, mathematical, just keeping things organized. So since we only have one independent variable right now, which is x, we can take this partial derivative and change it to a regular derivative. Okay? And so we have d squared t dx squared. Okay? The thermal production term is 0, and the steady state term is 0. And so now all we have is a simple equation: d squared t dx squared is equal to 0. Very straightforward. All right. So now we have this differential equation here. And we can solve this equation for a function t of x, right? Because remember, that's what we want. And so what we want from this problem is we want to find out how the temperature is distributed within that window pane, okay? Another way of saying this is that we want to solve for a function t of x, okay? Because that function t of x is going to tell us how the temperature distributes or how that temperature changes as a function of x. Okay. So in other words, we have a differential equation here. Probably a very, very simple differential equation, but a differential equation nonetheless. Okay. Okay. So the nice thing about this equation here is that we don't need any fancy techniques to do this. So no characteristic equation or anything like that. So we can just straight up integrate this. Okay. So we're going to integrate both sides with respect to x. Okay. So integrate the left-hand side dx, integrate the right-hand side dx. Okay. And so on the left-hand side, the integral is going to cancel out with one of the derivatives. And so on the left-hand side, after integrating once, we're just left with dt dx. And then on the right-hand side, since we're doing indefinite integrals here, so normally integral of 0 is just 0. But since we're doing indefinite integrals, we have to add an arbitrary constant. Okay. And in fact, we're gonna have another one. So I'm just gonna call this C1, just to kind of get ahead of ourselves. Okay. All right. So we're halfway there. We need to integrate one more time. Okay. So let me integrate that left-hand side once again with respect to x. Let me integrate the right-hand side here with respect to x. Okay. On the left-hand side, that integral is going to cancel out with that derivative. So all we're left with is t of x. Okay. And then on the right-hand side, we integrate C1. So C1 is a constant. And so you integrate a constant, you multiply it by x, right? So you have C1x. Okay. And then since we're doing another indefinite integral, we need to add another arbitrary constant, C2. So C2 is also an arbitrary constant. Okay, so this right here is the general solution to our temperature distribution. Okay. We're not done quite yet, but this is a good chance to kind of pause. All right, any questions on the math that took to get here? Okay, good. All right, so general solution is a good it's a good first step, right? So we always need to get this first before we solve the full problem. And actually, a lot of information can be found from the general solution as well. Right? The main thing that you can get from the general solution is you can see how the temperature distribution varies or the functional behavior. Okay. And so the fact that the only dependence on x that we have here is a linear one. Okay. This right here tells us that the temperature within the window pane is going to vary linearly across the thickness. Okay. So that means, a linear distribution basically means that, you're just going to draw a straight line from one end to the other. Okay. Okay. So now let's take this general solution and let's solve for the full solution. Okay. In other words, we need to solve for the values of those arbitrary constants. So, we're not just satisfied by saying that C1 and C2 are just arbitrary constants. We need to actually solve for their values. And the way that we usually do this is that we apply what's called boundary conditions. So boundary conditions, in a nutshell, boundary conditions tell us how our temperature, or those are conditions on our temperature field at specific locations of our domain. And the reason they're called boundary conditions that usually our conditions are known at the boundaries of our domain. Okay, that's usually where you can stick up the thermometer usually. Okay. So for this problem, we actually have two boundary conditions already. I just we weren't exactly clear with it from before. Okay. So let's go back up to the problem statement. And let's see, what information do we know about the temperature field based on the information that's given to us in the problem? Okay, so let's look at our geometry here. And in particular, let's look at the left-hand side and the right-hand side of the window pane. Okay. Let's look at the left-hand side first, okay? So the left-hand side here is telling us that the temperature of the window pane at x is equal to 0. So temperature at x is equal to 0. Okay. We know that, and we know that this temperature is actually T infinity. Okay. Then if we look at the other side of the window pane, and so we look at the location where x is equal to L, okay, so we have T at x is equal to L. Okay. We know that temperature as well, so we know that temperature is Ti. Okay. So let's take these two conditions and then let's apply them as our boundary conditions on our temperature distribution. Okay. So first we have the outside condition. Okay. So T at x is equal to 0 is equal to T infinity. Okay. So let's take this information and let's plug x is equal to 0 into our general solution. Okay. So our general solution here is C1 times x, but if we're plugging in x is equal to 0, this is going to be C1 times 0, okay, plus C2, okay. And we know, right, because C1 times 0 is just 0. Almost anything times 0 is just 0, okay? And so if we look at this equation here, right, we say T infinity is equal to C1 times 0 plus C2. So this tells us that our value of C2 is going to be T infinity, okay? Okay. So now let's do the same thing at our inside condition. So inside, we have T at x is equal to L is equal to Ti. Okay. So once again, we're going to plug into our general solution, but this time, instead of plugging in x is equal to 0, we're going to plug in x is equal to L. So you have C1 times L plus C2. Okay. Once again, we have an algebraic equation that we can solve for. Okay. So let's solve this equation for C1, since that's the one we don't know yet. Okay. So if I subtract C2 from both sides, I get Ti minus C2 is equal to C1 times L. Okay. We know what C2 is already, so let me go ahead and just plug in for that right now. Okay. So we already know from the first boundary condition that C2 is T infinity. And the last thing we need to do to solve for C1 is then divide both sides by L. Okay. So we have Ti minus T infinity divided by L. Is equal to C1. All right, and so now we have the value for C1, C2. Let's just plug it all in. And so now our final solution plugging for C1, C2, we have T of X is equal to C1 times X. So C1 we know is Ti. My iPad will behave. Minus T infinity divided by L, okay, multiplied by X plus C2, which is T infinity. All right. Any questions on this example here? Yeah. It depends. So some problems will give you numbers, and so if I give you numbers, you should plug in the numbers. Actually, we're gonna do one more example with numbers. But generally, what I like to do is I wait until the very end to plug in the numbers. So yeah. Yeah.
Is this a general form for, is this a pretty common situation, right?
Yeah, actually, that's a good observation. So we'll probably not get to it until Tuesday. But this situation of temperature on one side, temperature on the other side, you just have a solid in the middle is actually very common. So this actually leads into our next big topic, which is thermal resistances, which we'll talk on Monday. So or Tuesday, excuse me. But yeah, very good observation.
We don't care about the material because it's temperature's not changing at all.
Yeah, no, that's a great observation too. So notice how there's no thermal conductivity that appears here. So in a situation where you have fixed temperatures on both sides, it actually doesn't matter how much thermal conductivity you have because the temperature has to go from one to the other. Yeah. Okay. So last thing before we wrap it up for today, let's do another example just so you can see another heat equation problem. Okay. So this is going to be a very similar problem. So we're going to have a temperature through a medium, except we're going to add some additional wrinkles to it. Okay. Okay. So let's consider. So we have steady state conduction. Okay. through a plane wall. So this one's actually going to have numbers. And so let's say that the thickness here is going to be 50 millimeters. Okay. We actually have a value for the thermal conductivity here as well. So we'll say the thermal conductivity in this case is 5 watts per meters degree C. Okay. We'll say one side of the wall. One side of the wall is exposed to moving fluid. And so in other words, convection is going to be occurring there. Okay. The other side of the wall is going to be insulated. Okay. So insulated is a term that we'll kind of mention quite a lot in this class. Insulated basically just means that no heat can cross that wall, or we assume that no heat is going to cross that wall. Okay. Now, perfect insulation, I'll just make a comment on that really quickly. Perfect insulation is impossible. So it's impossible to perfectly insulate a surface. Whenever you have a temperature difference, no matter how good your insulation is, some heat is going to get through. That's just how it works. But mathematically, we can just make the assumption that things are insulated. Okay, so generally, when I say that things are insulated, I'll usually draw them with this kind of slanted line surface. Okay, so this right here is our insulated wall, or say insulated surface. Okay. On the other side, we have a moving fluid. Usually when we have a moving fluid in this class, I'll denote them with 3 arrows kind of parallel to each other. Okay. We'll say the temperature of the fluid that's moving, infinity, is 20 degrees C. Okay. And because the fluid is moving, we are going to have convection heat transfer. Okay. Now, I know we're not on the convection unit just yet, but convection is a very natural thing that occurs, in a lot of situations. So, we are still going to use it here. We're just not going to go too much in depth. Okay. So usually when convection occurs, we define the convection by what's something called the convection coefficient. Okay. So in a nutshell, the convection coefficient is just a number that describes how strong the convection heat transfer is.
Is that a material property?
It is not actually. So it's partially a property of the material, but it's also a property of the flow itself. Because generally, if you have faster moving flow, that's going to enhance convection heat transfer. So that's going to be the whole second unit. Is, how can we compute this convection coefficient? Okay. So for now, when we have convection in our problems, I'm just going to give you the convection coefficient. But there's a whole, we're going to talk about it for a whole 6 weeks of how how do we actually determine these coefficients. But for now, I'll just give it to you. So the convection coefficient for this problem, H is generally the symbol that we give for convection coefficients, is 500 watts per meter squared degrees C. Okay. It has similar units to thermal conductivity, except it's meter square instead of meter. Okay. That's because convection usually occurs across a surface. Okay. Okay. Other thing we know from the problem is that we know that the thermal conductivity in this solid is 5 watts per meters degree C. Okay. And by the way, there's thermal production here. Okay. Okay. I think we'll probably finish up this example on Tuesday, but at least want to set it up just so we can hit the ground running when we get there. Okay. Okay. So let's see. One last piece of information that we need before we move forward is let's assume we know the temperature of the wall on the left-hand side. Okay. So in other words, we know the temperature of the surface right here. Okay. Now you want to be careful a little bit. And so, the temperature of the surface is often different from the temperature of the fluid, right? So when you have a fluid that's kind of rushing past the surface like this, the surface itself is at a given temperature. And usually that's going to be different than the temperature of the fluid. Okay. So this T infinity here, this 20 degrees C, this right here is the temperature of the fluid. Getting a little bit crowded there. Let me do this. So let's say that the temperature of the surface is TS. And so we'll say TS here is 120 degrees C. This is temperature of the surface. Okay. And then T infinity we know is 20 degrees C. This is temperature of the fluid. Okay. It's very often those two are different from each other. Okay. Okay. So there's a lot going on. There's a lot going on in this problem. So let me just write out the problem statement, and then we'll wrap it up for today. Okay. Okay. So given all this information, given all that we know here, what we actually want to compute here is we're going to use the heat equation to determine what the thermal production in this medium has to be. We're going to compute. We're going to compute the magnitude of thermal production. Q dot. Okay. All right. So the process that we're going to go through for this problem is exactly the same as the last one. So we're going to start with the heat equation. We'll cancel out one of the terms due to assumptions. We'll solve it through. It's just that we're going to need to take it one more step because of the thermal production. Okay. All right, so a little bit more complicated, but heat equation is one thing that you kind of have to practice a lot. So we did a very simple example. Now we're going to do one that's more complicated, and then we'll go from there. Okay. Any final questions before we wrap it up for today?
The assumption we're going to have this.
Yeah, we're going to assume it's steady state. All right, so that's all we got time for today. So thank you guys for coming today. Hope you guys have a good weekend, and I will see you guys next week. Yeah. Yeah, because in the original heat equation, temperature can be a function of X and T. But since we crossed out this unsteady temperature, that T is no longer a variable. T is only a function of X and T.
Yep. We're getting a very good error. They need to plate support a week, but.
Yeah, the notes that you threw up before class, yeah. The recordings I usually post the day after.
Oh, yeah.
Yeah, back to back, like all four.
Oh, hi. Oh, hi, Jessica. Yeah, good to meet you.
It's awesome.
Oh, glad to have you with us. Yep.
Yeah, I'm pretty excited. Over here for.